Okay.
Okay, let's get started. So, just some logistics. If there's anyone taking the class that has not signed up yet for CAPTCHA, please sign up for the course on CAPTCHA. And similarly, the intro questionnaire, if you could finish filling that out by this week if you haven't. So, for the people that are still trying to get in, I wanted to see if people dropped, and we can wait a couple more days, but there were probably like 30 people that have emailed me over the past few months. So if you're still hanging on and in the class, so I don't have to go through 30 different emails, just send me a reminder saying you're still trying to get in. Again, I can't guarantee there's going to be good news. The numbers right now don't look like enough people dropped, but I will just say that if you're here today, you're hearing it in person because you're trying to get into the class, so just send me an email reminder so that I have the current list of people that are trying to get in. Okay. So we're going to keep going with these topics in supervised learning, and we started doing the perceptron. We're going to continue that to do the analysis, so the convergence proof, and then we're going to study decision trees. Okay, so feel free to stop me with any questions. So some of this is a review from last time. We talked about various ways where we could try to get a handle on the performance of perceptron, and generally to give a theoretical analysis, we have to start with some assumptions. So you could have an assumption that the data is perfectly separable, but not assume there's any margin. So all we're assuming is that the target, which is the true underlying classifier, dotted with the example, always matches the sign with the label of that example. You could also view it as U is the underlying perfect separator that is providing the labels YT for each example XT, right? Because if the label was negative and the sign of this dot product was positive, we'd get something negative, or vice versa. The only way to get something positive here is if the sign of this is exactly the same sign as the label. Okay, so we went over that before, but now we're just making it explicit with this underlying separator U. And for the analyses that we're going to talk about, we're assuming U is through the origin. But remember, this is not really a strong assumption. Just by increasing the dimensionality by 1, if data was separable with a linear separator, then in dimension z plus 1, it'll be separable with a linear separator through the origin. So for example, in your homeworks, if you're trying to fit a linear separator with perceptron and you don't know whether your data is separable through the origin, just take every data point and append one more dimension and set it to some constant value. So you can add sort of a comma 1 to every data point vector, and then you basically lifted it into one higher dimension. And so if it was perfectly separable with a linear separator, in the higher dimension, it'll be perfectly separable with a linear separator that goes to the origin. And since perceptron is trying to learn something through the origin, at least the simple version that we're using, you're probably going to want to do that. Okay, so I was getting to the geometrical interpretation. So all we've said is that the data is in Euclidean space. So this is the notation for the real numbers specifying the point in d-dimensional Euclidean space, and that there's some bound on the norm of every example. So just look at the largest magnitude example and figure out a constant that's greater than the magnitude of its norm, and then all the other examples live in a ball of radius capital R. So what we can do is, we're in dimension D, so we're in some high dimension. But we can project down to the plane. So we can project down to 2 dimensions. U is the normal vector to the perfect separator. The perfect separator is a hyperplane, but when we project it down, we're going to see a line. And we don't know U. If we did know it, we'd be done right. If we knew the perfect separator for all of our examples, xt, yt, we wouldn't need to do any learning. And so we don't know U. The algorithm is operating in green. It has some current separator here, and its normal vector is this v sub t. And it doesn't know U. So this gives us this geometric interpretation. We went through some animations last time. But remember, here's the rule. Perceptron is going to use this predicate statement. And if it fails, so if this is not a mistake, so if y has the same sign as our current classifier dotted with the example x, we do nothing. Otherwise, we do an update. So this will be negative only if y is the opposite sign of what our classifier gives. But the update is, take your previous classifier, add the new example, and the sign is given by the label. Okay. And note, we talked about how in online learning you want to update your classifier iteratively. So in this step here, inside the parentheses, I'm forming a prediction just by looking at y. So the prediction is the sign of vt.x. Okay? So I only look at y later to figure out if this is a mistake, in which case I make my update. Okay? So if a new data point comes in over here, are we going to make an update? So I want a yes or no answer and also a justification. Yes, somebody said, and what is the justification?
Because since it's below the ideal classifier, it should be classified as the class that's below, but because your separator sub t is not perfect, it's being classified as the wrong.
Right. So what is the sign of vt.xt? It's positive because remember we represent our hyperplane where the normal vector points towards positive examples. And yt, we know, has the same sign as u. U is the perfect separator that generates all labels. So what is yt for this example? Negative, because it's on the other side away from the normal vector u. So we're not going to see u, but we are going to see y sub t, which will be negative, but we've assigned it a positive label. In general, this whole wedge region, both on this side and this side, is our error region. Here our classifier gives a plus label, the true label is minus. Here our classifier gives a minus label and the true label is plus. If we saw a positively labeled example over here, we would not make an update. If we saw a negatively labeled example over here, we would not make an update. We only make an update in this error region. So in high dimension, this is a hypersphere with these wedges, and then when we project it down, we get these wedge regions, which are the error regions. And so those are the places that we're going to make the updates. Okay, so that was just a reminder, slightly different animation. So, so this is one possible assumption, that there's perfect separation, but we're not assuming any margin. We're not assuming any separation between the two classes. Okay, so under this assumption, and also the assumption that X is actually uniform on the hypersphere, then there are various results that have been shown. So if you want to get error rate less than a threshold epsilon, the epsilon is the threshold that you want on your error rate on your training distribution, then these are various bounds. So here's sort of a positive result. So you need the dimension divided by epsilon squared mistakes to reach that error. In some work that I've actually worked on, we also showed a negative result, that you can't actually do better than needing it at least 1 over epsilon squared mistakes, needing to make that many mistakes to reach error epsilon. And then also something for active learning, which we're not going to get to until after the midterm when we study advanced topics. So other than this result, though, this is not the standard way that Perceptron was analyzed. These are some more recent results. The standard canonical way where you could get a good result for Perceptron is you make a stronger assumption. You make that margin assumption where you assume all the positive examples are separated by all the negative examples by a certain amount. So this assumption should look extremely familiar on the left side, but instead of just saying greater than 0, we lower bound by a constant greater than 0. So draw a picture. So if we have that u dot x times y is greater than 0, the situation is that, you know, all positive examples are above this decision surface given by u, and all negative examples are below it. But we're not making any claims on the closest distance between pairs of positive and negative. This is called, you know, perfect linear separability. But what is called a margin assumption means that on the right-hand side we have a constant greater than 0. Okay, so we have some gamma that is strictly greater than 0. Oh. Do you think it's charged, or yeah, fully charged? So maybe I'll just. I'm gonna probably walk around. So what it means is, with respect to u, so this distance is gamma and this distance is gamma. All the pluses are above, and all the minuses. Oh, sorry, this was just a dotted line. These were not minuses. Okay. So this is a stronger assumption. So without this assumption, we have some newer results, but with this strong assumption, we can prove something easily together today in class. Okay, so we're just going to, it would be like saying you had this assumption, but when you zoom really close in, there's some constant greater than 0 length that separates any positive example from any negative example. Okay, but it's, you know, it's a stronger assumption because we have a strict greater than 0 here. I mean, we have a strict greater than 0 here, but it's not for any fixed gamma. This is just greater than 0. Okay, so this is called the margin assumption. And we're going to show this. This is a more famous analysis of perceptron. So when people ask you about the perceptron convergence analysis proof, they're usually talking about this one. Okay. So any questions about this assumption? We're saying not only does U have the correct label, meaning that the sign of this thing is positive, but it's lower bounded by a positive constant. So there's a gap between the decision surface and any positive example. Similarly, there's a gap between the decision surface and any negative example. Okay. Any questions about that assumption? So note that actually neither of these assumptions hardly ever holds in practice. Okay, but we prove what we can with assumptions that are as reasonable as we can make them. So we prove something in this nice scenario, and then we hope that even in practice where it doesn't hold, it works most of the time. Okay. Okay. So I'm just rewriting. This is the important margin assumption here. We want to prove that the algorithm will make at most big O of 1 over the margin squared number of mistakes. And we're going to prove it as follows. So we're assuming some upper bound on the norm of every training example X. This is with lots of generality, but if you have a batch of training data, as I said, you can go through the whole batch, compute the norms of all of them, and set R to be the max norm value, or a little bit larger than the max norm value, okay? This assumption is without loss of generality, okay? Because you take your perfect separator, if it has some norm that's greater than 1, just normalize it, right? So divide the vector, every element by its norm, then you get to a norm 1 vector. So again, this is without loss of generality. This is with some loss of generality, but I'm just going to call R the max norm of any data point. The reason why it's with loss of generality, though, is that usually you have infinite data sets, right? And I think last time I said that V0 was the first classifier. For my off by 1 issues to work out, let's have V1 be the first classifier, and I'm going to initialize it to be a vector of V0. Okay? And I only need to, it's essentially various things that we're doing are proof by induction, so I only need to show one update step. And so I don't actually need any subscripts on my X and Y. I'm just going to have them be an XY pair that is a mistake, meaning with respect to the current classifier VT, this mistake condition holds. Okay, so the sign of VT.X is not equal to the sign of Y, so you get negative. Okay, so I basically just need two facts, right, for these lemmas. So this is one of the lemmas. Okay, so I would like to prove the following, but so I can start with the left-hand side. And I can go ahead and look back at the definition of the algorithm, right, to know what the VT plus 1 is. So this is simply U dotted with VT plus 1. What is that? That's VT plus, Y dot YX. So Y is a scalar, it's not dotted. I've dropped the subscripts because, again, I just said that for the sake of this lemma, X comma Y is a mistake with respect to VT. Okay, so wherever I have vectors, I dot, right? And again, Y is a scalar. All right, so how do I finish off? How do I show that this last step holds from here? So I just started, I'm moving over so that people can see, but I started with the left-hand side. This is, by definition, VT plus 1, right, from the algorithm, in the perceptron algorithm. this is just multiplying through linear algebra. Okay, and then I'd like to take the final step. So what do I need to apply? Right, so this is greater than u dot vt plus gamma by the definition of the margin gamma, right? So the thing that we applied is this very important margin assumption. If we didn't have this, we couldn't do this final bound here. Okay. So any questions about any of those steps? Right. So here's the left-hand side. I plug in the definition of VT, multiply it out. These are just to be dots, like in the middle, not periods. And then this is by definition of gamma. Okay, so this is one of the facts that I need. Questions? Okay, so the other thing I'm going to claim is this statement. Okay. So just a couple of facts, right? So if you have, this is the Euclidean norm, also known as the L2 norm. So this is the square root of x dotted with itself. Okay, so there's a lot of ways to write this. Okay, so if we square it, we just get x dotted with itself. Okay, so I want to take the left-hand side and expand it out. Right. Okay, so the left-hand side is VT plus 1 norm squared. So again, I can just plug in the definition of VT plus 1 coming from the perceptron algorithm, VT plus YX. So this is by perceptron algorithm. Okay. And the other kind of fact I wanted to show from before is if you have a plus b squared, right, this is the dot product of a and b. What I'm doing is I'm just plugging in the quantity a plus b for x over there. Sorry, it must be confusing. Right, to go from the norm to the norm squared, I just square it, I lose the square root. Okay, so this is a dotted with itself plus b dotted with a plus a dotted with b plus b dotted with itself. But again, this is just norm squared. Dot product is symmetric. Right, so we have 2a dot b and the norm of b squared. These again are substitutions from what we had over on the other side. So that's all that's happening here. This is my a, this is my b. So I get the norm squared of vt, the norm squared of x, and then I get two of these terms where I have a constant times a dot product. Okay. Any questions about that? So here's one substitution, right? What did I do here? Here I just applied the upper bound on the norm of x, right? All x's in our training data have norm bounded by r, so the norm squared is less than r squared. And then how would I take this final step? I'm almost there, but I want to end up here. What can I use? So what do I know about x, y? It's a mistake. What's the definition of mistake? Right. So so this is less than 0, the negative number. 2 times it is also a negative number. So all I'm saying is, this is negative actually. So this is less than or equal to the norm of VT squared plus R squared. Okay. So any questions about these two lemmas? These are sort of the basis for where we're going. We've shown they held, basically, each of them is now a recurrence, right? It just holds as you go from VT to VT plus 1, no matter what your T is, These are T's in terms of the number of updates that you've done to your classifier. Okay, so now we're going to kind of put these all together by expanding out the recurrence. Okay, so lemma 1 gave us the following recurrence. This is pretty straightforward to see, but we can just expand it out, right? So lemma 1 told me, right, VT plus 1 is greater than or equal to U dot VT plus gamma. Okay, so now I can just apply lemma 1 again. Yeah?
I think it should be U dot VT plus 1.
Oh yeah, sorry. Thank you. So I just want to apply, this is lemma 1. And so we can now apply lemma 1 to U dot VT. So what do we get? So I make this substitution. So this thing is greater than or equal to what? So what is U dot VT greater than or equal to by applying lemma 1?
U dot VT minus 1.
Yep, U dot VT minus 1 plus gamma, right? So I keep getting these, and then finally U dot V1 equals 0 because V1 was initialized to be a vector of zeros. So we're going to get a certain number of these. So for U dot Vm plus 1, we're going to get m factors of gamma. Okay. Any questions about that? So using identical logic, we expand out the recurrence in lemma 2, and we get this. So people see that? The logic is identical. But then I'm just going to go ahead and take the square root of both sides. So I lose the square on the norm, I get the square root of m, and I lose the square on r. Okay, so any questions? Okay, so we're going to do one more thing, which is by Cauchy-Schwarz. So there are some important lemmas that you should remember from linear algebra that come up in machine learning. So this is one of them. Right, so Cauchy-Schwarz is saying that for any two vectors, the following property holds. Okay. Now, in our case, what is this equal to? What can we apply to simplify this a little bit? U has a norm of 1 in our case. And also, to be completely general, any number is always going to be less than or equal to its own absolute value. Either the number is positive, in which it equals its absolute value, or it's going to be negative, in which case it's less than its absolute value. Okay, So in summary, we have UV is less than or equal to the norm of V, and we're going to use this for the n+1 version. Okay, so that's kind of at the crux of what we're going to use. And then we're going to apply A, which we derived from lemma 1, and B, which we derived from lemma 2 on both sides. Okay. Right. So A is saying that this thing is greater than or equal to m delta. Remember, this is Cauchy-Schwarz, this inequality. And this we upper bounded using the result from lemma 2, right? And then taking the square root of both sides. Okay, so this was from lemma 2, from lemma 1, and this was from lemma 2. Okay, so questions about either of those. All I'm doing at this point is just plugging in this and this, which we derived. Okay, so I kind of want to finish off over here. I can look at both sides here. So I get root m is less than or equal to r over gamma. And I can go ahead and square that to get m is less than or equal to the quantity r over gamma squared. So what is this? So this is saying we make at most r over gamma squared mistakes. So if we have an upper bound on mistakes, it means after we make those mistakes, that many mistakes, we don't make any more mistakes. That's a great error convergence guarantee. So this is, remember r is a constant, so this is big O of 1 over gamma squared. Okay. So what you're saying is, if I start with data that is perfectly separated at margin gamma, then after big O of 1 over gamma squared mistakes, you know, I have perfect classification on my data set. Okay. So any questions about any steps or anything that needs to be clarified? Or something that you can't see? This is all on the slide. I would just, sometimes it's better to do it by hand to slow down, but it's all summarized on the slide. Okay. Let's show some application of perceptron. We can do a simple example from biology. So this was an example in studying flowers, and you can measure a lot of different features like lengths of various aspects and petal lengths, widths, etc. And so there's the iris flowers, where there's 3 different species of iris flower with these 3 different names. Okay, and he just measured 4 features: this sepal length, sepal width, petal length, and petal width. Okay, and this was an early paper about using linear classification for this problem in biology. Okay, now D equals 4. We measured 4 features. I want to show you the data projected onto the screen, so I'm going to show you projections between pairs of features. So here's sepal width versus sepal length, and there's 3 different classes here. So we're going to have circles for one kind of iris, pluses for another kind of iris, and stars for the third species. And then you can look at projecting onto the other features, the petal width and petal length. Okay, so on the first projection, you can use standard perceptron and get, this is actually perfect separation of Setosa from the other two classes. And so the number of updates was 1,500 if you just take the data as given, but you can find under different permutations, such as random permutations, a convergence that's a little bit less. Okay, so an example of using perceptron on a linear classification task. This task over here looks pretty simple if you just want to separate Setosa, these circle ones, from the other two classes using these two features. And indeed, the number of iterations for perceptron to converge on this was only 2. So these are the points by just the number in the list of points that where it made errors. So at the first iteration, it was making errors here and here. So maybe the separator was more like that. In the second iteration, it made classes on error on both of these 2 points. And by the third iteration, it didn't make any error. So from the visual inspection, you probably thought this was a very easy binary classification task. And this is borne out by, perceptron solving it pretty quickly. Okay. So this is Setosa. One of the other classes is called versicolor. And what if I want to separate it from the other 2 classes? Well, the data is not linearly separable, even in 2 dimensions. So it doesn't seem like we could fit a line anywhere that separates out all the stars from all the pluses. Okay, so linear separation was a good starting point. We talked about perceptron. We did perceptron convergence rate and proof, but we're going to move on to other kinds of classifiers. So the first one is decision trees. And this is actually well motivated by the flower problem, because we had 3 different classes of flowers. It doesn't only have to be for binary classification. The representations are simple. You can get very good classifications, and they're very interpretable and understandable by humans looking at the classifiers. And so we're going to talk about how to build them. So this is a decision tree where you come in and you compare your petal length to some threshold. If it's less than some threshold, you'll say the class is Setosa, etc. Then you look at the petal width, compare it to a threshold classified as Virginica or not, in which case you might need to go down into lower levels of the tree. Okay, so really we want something, so I'm looking at petal length and I'm comparing it to this threshold 2.45. And actually, that's great. I'm done in terms of Setosa, right? Because all of this class, these ones with the circle, have petal length less than 2.45. So petal length is the X on this example. Now I'm done over here, so I can recurse on this section. And I want to make some split that does a pretty good job of narrowing things down. So if I look at the y-axis and split above 1.75, everything above that is this other class, Virginica, right? I have complete purity here. There's no stars or circles in that. So these guys can get classified pretty soon, but I kind of have a mixture in here. So now I'm going to recurse in here. So you could do a split here at 4.95. So there's going to be some error. You could say, all right, if it's greater than that, it's Virginica. This would actually make 2 errors. This also would make 1 error. And then recurse, etc. So here you get a pretty good classifier. This classifier makes 1, 2, 3 errors on this whole data set. Okay. So decision trees is a topic, and just like a lot of topics in machine learning, there have been a lot of approaches. We're going to first talk about one of the most canonical approaches called KD trees. And this is actually an instance of a KD tree. So we're just going to be concerned with rectangular regions or their generalization in high dimension. So regions that are separated by axis parallel hyperplanes in high dimension. Okay. And we're going to cycle through the dimensions, make a cut that splits at the median on the particular dimension, and then recurse. So here we're considering the x dimension. We find the median, meaning we want half the points on each side. We make a split. So this is not even looking at the class labels. We just want half of the total number of points to be on each side, and recurse along the next dimension. Etc. This is also a good technique to create a nearest neighbor data structure. So you've already heard about nearest neighbor. So you have a lot of data in high dimension, it's labeled, and you want to pre-process it in such a way that if a new data point comes, you can quickly query for its nearest neighbor. You don't want to use the techniques of lecture 1 where you have a search engine across the entire